I am Arno from ThinkCell. We have the booth outside. And I'm going to talk about it from iterators to ranges. To get to know my audience a little bit, let's start with a few questions. So, who knows Boost Range, the library? Okay, quite a few of you. And who knows Eric Niebler's library? Okay, about as many. And who already uses ranges when you are programming on an everyday basis? Okay, cool. Let's see, what are you using? So who is using Eric's library? Who is using Boost Range? Okay, Boost Range seems to have the edge there. Interesting, okay. Well, first of all, why should we use ranges? There were about 10% of you or so who are using ranges. I think everyone should use them, because it really makes life a whole lot easier. So how are we doing it in the era before ranges? You would write something like this. You have a std vector, and you want to remove the duplicate elements. How do you do it? Well, you first sort the vector, std sort vec begin vec end. So there we already have vec twice in there. And then you run vec erase of std unique, vec begin, vec end, vec end. I think we mentioned vec 5 times. That's far too many. And really what we should have is that pairs of iterators, they really belong together, right? We're talking about one entity here. So we want to put them together into a range. But before we talk about this a little bit further, there is a bug in the code up there, and I want you to tell me what it is. So we got sort, vec begin, vec end, and then erase, unique, begin, end, end. There is a subtle bug in that code. It almost works. Okay, I'm missing maybe some parentheses. That's not the bug I was talking about. What is std sort using to sort a range? The std less, the less operator. Okay? What is unique using to throw away elements? The equal operator. And there's the bug. If someone implements these things inconsistently, which, yes, you should not do, but imagine we do this in a library, and you don't want to make life unnecessarily difficult, you should really use for throwing away elements, for the std unique, you should really not your less operator. Really, this operation of throwing away duplicate elements should run on a single predicate. And this is something actually you can do when you're using ranges. We not only have the rangified, unique in place sort idiom in our library, we also have a sort unique in place that basically does the sorting and then throws away the elements in one go, and it actually makes sure that you are using a consistent predicate. So these kind of things you can also get when you use range libraries. More consistent and arguably correcter code. Why do I think I know something about ranges? So we started with Boost Range, using Boost Range in our code, but this evolved very much into our own range library that is public, and I will show you the GitHub at the end. We have about 1 million lines of production code that uses that library. And we have one big luxury. We have the library, and we have the code. And we actually have one guy who does nothing else all day but refactoring code. So if we think something is wrong about our range library, we can change it at any time and change the 1 million lines production code along with it. So we learned a lot. By evolving that library, we learned how a range library should look like. Which things produce mistakes, which things are idiomatic, which things are intuitive to use. And some of that I want to tell you now in the code. What do we have right now in terms of ranges? Well, turns out not much. In the standard, we have, that was in C++ 11, not much has changed in C++ 17. We have the range-based for loop. And that essentially works on anything that has a begin and an end. We also have universal access to begin and end, this std begin and std end, which unfortunately doesn't quite work because they forgot to add the ADL lookup. So if you want to add a begin and end to an existing type, you have kind of a problem, because you would have to basically, when you write it into the same namespace as that type, it won't be found by std begin std end. So really, you have to write using std begin and then begin. That's kind of the idiomatic way to use std begin std end, because they don't do it internally. And that's all. That's all we have. There's going to be more coming up, and the future of ranges is really, as far as the standard is concerned, is by and large Eric Niebler's pet project. He is driving that, and I'm thankful for it. So the first thing that is going into the standard is going to be the technical specification ranges. It essentially for the programmer adds by and large the algorithms we already have in the standard library, which currently take iterator pairs as range versions. So you then can invoke it with anything that exposes begin and end. That's not a whole lot. The real thing that Eric would like to standardize is in his library, the range v3 library. It contains quite a bit more. And before we go into details, let's clarify what ranges are. Ranges are anything that has, for the purpose of the standard right now, anything that is a begin and an end. That, of course, can be your plain vanilla containers, vectors, strings, lists. These containers, they're usually owning their elements. So when you throw away the containers, the elements get destroyed. They have deep copy semantics. So when you copy the container, the elements get copied. And they have deep constness. So if you have a const version of the container, then all your elements are const. You can't modify the elements. You think, well, that's quite natural, right? I mean, that's how it should be. Well, not quite. There are views, and views are quite the opposite. It's like, well, what does that mean? What's quite the opposite mean? Well, think iterator pairs. Iterator pairs, they don't own their elements. When you copy the iterators, the elements stay untouched. And when the iterator itself is const, that does not influence whether you can access the elements const or not. And this is really, these same properties, these other ranges have, which are called views in the standard. And a simple implementation of such a view is here the iterator range. You basically have a pair of iterators encapsulated into one object. Easy enough. Well, if that would be the end of the story, that would be a little bit sad, and that wouldn't be quite enough to justify an important change in the standard. But there is more. And to motivate that, let's look at this problem. Let's say you want to have a vector again, and you want to find of ints, and you want to find an element, say 4, in that vector. You would write something like find vector 4. Okay, clear enough. Let's say you want to do the same thing again, you want to find a 4 in a vector, but that vector doesn't contain ints directly. It contains the ints embedded in some larger structure. And really what you want to do is you want to do a projection of the structure onto the int that is contained in the structure, and then look for the 4 in that projection. Now, the way to write that, if you have nothing else, would be with a find if and then aid equals 4, as you see in the bottom, at the bottom. But it's kind of ugly, because arguably these two things are very similar in semantics. You're looking for a 4 in a list of ints. Just the nature of this list of ints is different. But when you look at the syntax that we use, it's very different. There's nothing to do with one another. And ranges are out to change that. Enter the transform adapter. And the transform adapter is probably one of the two most important range kind of innovations you will use. What it does is you can transform a range, a given range, with a given function. Down here, you are doing a TC transform of the vector, and you're plugging in a std memphen that extracts the ID from the elements of the vector. The important thing here is when you are invoking transform, when you're running the transform call, nothing happens. The vector gets wrapped into an object, but nothing gets executed. The structs, the elements stay as they are. And only when you then iterate over that transformed range, you will actually, with every dereferencing of an iterator, you will actually invoke your function, your mapping function, and do the actual transformation to the end. And when you do that here for our problem, then suddenly things look quite more similar. So you have range find on top, and you have the range find at the bottom just as well. So, but in this case, you're doing your find on the transformed version of the vector. So we have separated our algorithm, the find, from the thing we are finding in, from the projection. How does this transform adapter, one more little subtlety down here. In both cases, I just naively assigned the iterator that we found to it, right? Now, what does it point to? Here's the same code again. Well, it, of course, points to int, because our find runs over a list of ints, so the iterator that it passes out is an iterator to int. Well, very frequently, that's probably not what you want. You kind of want to go back to your source of your transform. And so you want to point, it should point to a instead of int. So in this case, the library offers something like a .base, where you can go back from the iterator of the transformed range to the iterator of the base range, in this case, the vector. So the it down below would actually point to a's. Here's how a transform adapter is implemented. If you do it naively, you basically, your struct may contain just two iterators that are transforming while they are being dereferenced. And for them to do that, the iterators need to contain the functor, and of course they need to contain a copy of the iterator. And then, as you can see here, the dereference simply applies the functor to the dereferenced iterator, the base iterator, and passes the result out. And the base just gives you the encapsulated iterator. Okay, that was number one. That was the transform. Here's number two, the filter. These are really the two big ones. If you count the number of occurrences in the code base, I think they dominated about 80% of the use cases or so. So let's say this time we want, again, the vector. It contains, again, our struct A. But we want to restrict it to the A's where the ID is 4. So we want to filter the vector for all the things where the ID is 4. And this is how you write it. So again, the TC filter just produces an object that exposes that range that you can iterate over. Nothing is happening yet. And only when you actually need elements, then this thing is running, or is actually doing some filtering, which is good if you, for example, only need the first element, right? Why would you filter the whole range if you only need the first element of it? And this is doing exactly that, so it's nice. Now here's your filter adapter implementation. So if you do this in the kind of naive way, you start with the filter range, which again contains iterators. And for the iterator to do its job, it again needs a few things. One is the function that you want to do the filtering with, and the other one is the iterator. Well, there's a little caveat here. You also need the end iterator. So you need to store two iterators inside your iterator. Why? Well, when you're starting to filter and you're throwing away things, then at some point you may reach end. So everything, say, before end got filtered, and now you're standing at end. You need to know when to stop. Otherwise, you're going to inadvertently dereference the end iterator, still looking for your element. So you need to know where to stop. And thus, you need the end iterator. Okay, that's kind of cool. Well, How does the iterator look like? Of a filter, of a filter, of a filter. Like this. So when you are, it's quite natural to stack these things. You get a range from somewhere. You don't really know where it comes from in your generic algorithm. And so then you apply another algorithm to it, a filter say, and suddenly you get double the size of your original iterator. Well, you do this 5 times, and you're moving like 200 bytes large iterators through your program. That can't really be very efficient. And for everyone who is using boost range, they do that. We pointed that out to the standard, to Eric Niebler actually, and they did something in the standard that helps out a little bit. They said, okay, we are going to require that as long as you are using an iterator of a range, that range must stay alive. You must keep that range around. Your range must not go out of scope, and you are still using the iterators, kind of like how it is with containers. And this is actually in the standard, and that helps a lot, because what you can do is you can store all the stuff that is the same over all the iterators, the functor and the end. You can store that inside your range object. So you move that into the range object, and your iterators are just containing the base iterator and then a pointer to their range object. And whenever they need the end iterator or the functor, they go to the range object and get it from there. Consequence, iterators cannot outlive the range. And this is now what you get. Well, it's still not insanely great. So your outer iterator contains a pointer to its range object. But then, of course, the base iterator again contains a pointer to the base object, and so on. So you still get this linear growth in the size of iterators. And that's range v3 / standard state of the art. That's all they have. Well, we didn't like it. So what can we do better? Let's introduce a different concept, which is a little bit like an iterator. I call it an index. Some call it, I've heard position as a name for it. It has been around, and the idea is really whenever you are doing an operation on that pseudo-iterator, you're not going to do it directly on the iterator. You are going to do it on the iterator in combination with its range object. So when you're incrementing, it's maybe implemented as a function on the range. Please increment that index. Please decrement that index. Please dereference that index. And you always have to supply both of these things, the range and the index. And it's like, well, that's kind of a departure from existing best practice, right? We're used to iterators, so that's not really great. So how does that help, right? Why do we do so complicated? Well, first of all, let's deal with the legacy part. We want iterators instead of these indices, and where we have 2 objects to deal with. Compatibility is relatively easy to achieve. So first of all, any iterator can be used as an index. So if you want to wrap the vector into something that supports that index concept, that's easily done, because any iterator that can do these things by themselves will serve as an index just fine. You just can ignore the range object information and just operate directly on your index / iterator. So that's okay. Now, the other way around, if you have an index and you want an iterator, that's also pretty easy, because essentially any index you have, you can always wrap together generically into an object that is holding a pointer to the base range and encapsulates, aggregates the index. And that you can do for any index that is out there. In fact, that's what's happening in our code. Our user code is still written with iterators just like before, even if underneath we use something else. And now the question is, well, okay, now we can introduce these indices without too much compatibility problems with past code, but how do they help? Well, they do help greatly. You can do something like this. If you have an index-based filter range, inside your filter range, you again store your functor, and you store not the end iterator, but a reference to the base range, to the range that you filtered. Now your increment index that takes an index and increments it can be implemented in terms of the increment index of the base range. And as you can see, the index of that filter range is then exactly the same type as the index of the base range. So you don't add any extra memory requirements to these adapted iterators, to these adapted ranges. Whenever you are iterating over them, the iterator will then be the wrapped index, and that will basically contain two machine words, one being the index, kind of like a pointer, and the other one being the pointer to the base range. So you're getting by with two words, regardless of the stacking depth. That's kind of cool. Now, here's that again. Here's another difference from what we are doing versus the range v3, which is likely to go into the standard. The standard makes a very strong distinction between views and containers. So containers are containing their elements, and views are just referencing elements. They have that kind of the iterator semantics. Sounds like a good idea. The problem that arises is the following. Say you do this, looks all good, so you filter your vector with a predicate, and the filter object will just aggregate a reference to the vector. So as long as your vec stays alive, everything is honky-dory, and you can do it just like I wrote here. Now, let's change that a little bit. Let's say the vector was created in place. And when you're programming with ranges, you actually do this very often. Your urge to inline is quite big. You don't need to name that stuff anymore. You just say, okay, I'm just going to generate a vector, and then I'm going to filter it and transform it, and la, 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 la. And it's all fine. Except that if you're now doing what we did before, we store a reference to that vector that we passed to the filter, well, that reference is going to go out of scope. It's going to dangle because the create vector is going, the vector that's being created in create vector is going to go out of scope. So what do we do? Well, range v3 says just don't compile. Disallow that because it's dangerous. The thing is, people will try to make things compile. And the alternative that the range v3 library offers is this. There's not a view filter, but it's an action filter. How is that different? Well, it works with R values, but it's also eager. It will take the vector and do the filtering right then and there. It will filter the vector, and the auto range that we actually assigned will actually be the filtered vector. So it is very tempting to replace this with that, but you lose potentially a lot of performance. If you only need the first value of that vector, you just filtered it all, and then you just take the first element, and that's it, and throw the whole thing away. Quite inefficient. And I think that's dangerous. That proved in our code base that that was an untenable situation. It's not lazy anymore. So what do we do at ThinkCell when you run into this R value problem? If the adapter input is an L value container, so if it's a reference, then the filter will create a view. It will just reference that L value because presumably it will stay in scope. It's kind of transparent that you're holding a reference there. And then the view is a reference. Now, if the adapter input is an R value, if it has just been created prior to calling the filter, then the filter will automatically detect that, will say, okay, this is an R value reference, and will generate a different type that aggregates that R value, that copies the R value into the into that object itself. And it will actually be a container. So you will have a container that has deep copy semantics, it has deep const, and it's owning its elements, but it's still lazy. And that's kind of, I think that's kind of important. There is the laziness aspect of ranges, and then there is the range aspect of ranges, the sorry. There's the laziness aspect and there's the container aspect. And these two are by and large orthogonal. You can have one, but you don't have the other. And I think that's something that's an important feature to have. Okay, let's go on. Now, so far we played around already with that find, and if you have ranges, it's kind of tempting to say, okay, isn't there? It still returns an iterator. It's we're living in a range world, and maybe it's sometimes more useful to actually return a range. So let's look at this. What this pack actually is doing, we introduced another template parameter into the pack, into the find, which controls what the find is returning. And really the find has two situations. One is I found something, great, what do I return? And the other one is find didn't find anything, what am I returning? And by default, in the first case you return an iterator, in the second case you return end. It's not really clear to me why you are returning end. It's by and large an arbitrary choice. And what you may want to do instead is things like that. I don't know how often you've written a find with an assertion afterwards, oh, I don't want this to be end, because I know that that element should be contained in the vector, or in the thing that I'm finding it. And you don't have to write that assert anymore. What you can do actually instead is you can just say, hey, don't say return iterator or end, but I just want return iterator. I don't think this or end case is a valid case. This is an assertion, this is an invalid state in my program. And now you basically can annotate your find with that expectation. You can annotate it with what you actually want. You can go one step further. Well, if we can best specify what we are returning, then we may as well do things like that. Say we return the head. We return everything from the beginning to what we found. And you may as well have return head or an empty range, or return head if you didn't find anything, return empty. Or if you didn't find anything, you return everything. So you can specify what kind of return you want from your find. Now, let's go away a little bit, or let's extend a little bit the definition of what a range is. So far, it's anything that has a beginning and an end, that you can get iterators from and iterate. But there are other situations where you have something that is like a range, where you are enumerating values, but you don't really naturally have an iterator. Here is, I have as an example, traverse widgets. And known as a visitor pattern, so you pass a functor, and that functor now gets called with all the elements. Easy enough. Let me drink something. Okay, hope that gets better now. So, right, so this is you passing a function, and that function gets passed all the elements that you want to enumerate one by one. And the thing is, it would be kind of hard to write an iterator for that because it's recursive. So you're having a window and you're traversing its widgets, and the widgets may contain sub-widgets, and it's a bit like a range, but it doesn't have any iterators. But still, maybe you want to use it like a range. Let's see how this works. You may want to write something like this. Did the mouse had any widgets? Well, that's like a natural any-off, right? You go through all your elements, and then you say, okay, does anyone of these widgets got a mouse hit. Now, the natural way to do this is to change the way we iterate. Usually what we do when we iterate with iterators is we have the consumer at the bottom of the stack and the producer at the top of the stack. So the consumer calls *it, and it calls into the iterator to generate a value, and that then returns, and you have your value. Then you do some processing on it, and when you need the next value, you again call into your iterator, and it returns. So consumers at the bottom, producers at the top. This has consequences. Consumers at the bottom of the stack. So it has actually a contiguous code path for the whole range. So you can write your code anywhere, and whenever you need a value, you say, hey, I need a value, and you get a value, and then you need the next value, you get another value. So it's very easy to write that as a continuous control flow. You get better performance because in an iterator, you kind of have to restore your state. You need to know where you are to get the next value. If you are in a continuous control flow, the state is encoded essentially in your instruction pointer of your iteration. And you also have no limit for stack memory. You can basically remember as much as you want on the stack while you're iterating, because your stack actually stays around during your iteration. For the producer who's at the top of the stack, so if you're writing an iterator essentially, it's different. Your contiguous code path is only for the single item. When you're going to the next item, you had a return, and then you get called again. It's harder to write these things. Imagine you have to traverse a tree. It's pretty trivial as a contiguous code path. You just make recursive calls. Well, if you had to write an iterator for that would be quite a bit harder. And you can only remember so much in your iteration, inside your iterator. You have a fixed amount of memory, or you have to actually go and allocate the memory on the stack, which is somewhat inefficient. So that's a problem you don't have when you sit at the bottom of the stack. So what we basically did, and actually this thing is named external iteration. That's the computer science name for that kind of iteration, as opposed to the internal iteration. What do we do during internal iteration? Well, we turn this whole thing around. We put the producer at the bottom of the stack, and it calls into the consumer whenever it has a new value. Now, all the advantages and disadvantages are just the other way around. No surprise. And again, nothing magic. But it turns out, before I go to the consequences, of course, I said that to be at the bottom of the stack is great. So all these advantages. And top of the stack kind of sucks because you have a lot of disadvantages. Wouldn't it be nice if you could both, the consumer and the producer, could be at the bottom of the stack? Well, they can be with coroutines. Coroutines are kind of would work like this. You are the traverse widgets. Whenever it's enumerating a widget with the yield command, it would kind of pass the next element over to this other coroutine or thread, and it just continues. So it's kind of a ping pong game. Like both the producer and the consumer both run along the same thread. Or run their thread of execution, and whenever one has a value, it just passes over to the other one, and when there's the next one wants the same next value, it tells you, hey, give me the other one, and it continues to the next point where it actually has a value. So it kind of runs, and they just continue their execution to generate the next value. Okay, that's great, but it's hard to do. So either you need two complete stacks, which is kind of like two complete threads, fibers, really. They are fibers is kind of threads, but you don't get the automatic execution. It's a cooperative threads. But usually they have to have their own stack, so you need virtual memory for a stack. So it is a pretty heavyweight thing, which if you only have to do and we are talking small loops here that we want to optimize. And to do that with such a heavyweight thing is not going to be very performant. There is an alternative, stackless coroutines. They have been proposed in N 4402, and there they kind of simplified the problem of generating these things by restricting the yielding to the topmost function. And there, this is much simpler because the amount of stack you need can be calculated in advance. Essentially, the compiler knows how much stack a single function will take up and can allocate that function somewhere as part of your iterator, if you will. And that will actually make it possible to run generators as without actually generating or having two stacks. Again, even stackless coroutines are a little bit expensive. You have dynamic jumps to the resume point. You have to save some registers when you're yielding. And I don't think anyone can do aggressive inlining yet for these things. The big disadvantage is also you don't gain quite as much as with the stackful coroutines, because you really have to be these recursive patterns with the yielding for the widgets that I showed relied on the fact, and that's frequently the case, that you have a recursive callback. And recursion, of course, is out of the game if you can only yield in the topmost function. And it turns out, going through our code base, that internal iteration actually is often good enough. You can't run a find, because at least as long as you're returning iterators, you can run a find if you only need the value. Then you could just return the value. You can't do the binary search, again, same reason, but you can do a for each. Actually, the for each is kind of the primary thing where you really turn the external iteration into an internal iteration. You say, here's my body that I want you to call for every one of my elements. Well, this is exactly what internal iteration is doing. So the for each is a very natural, and it's very frequent. I mean, most of these things are for loops, are for eaches that we are using ranges for. You can do accumulate, you can do all of, any of, none of. So many of the algorithms that we are running are actually happy with internal iteration. So it seems silly not to support it, because it is performance-wise and it has advantages. Let's look at adapters that I showed you previously, where adapt the ranges. You can do them with internal iteration. You can do the filter, you can do the transform. So how does a filter as internal iteration looks like? Well, you get called from your range with a new element. Look at the new element, you say, is it good? If it's good, you pass it on to your consumer. If it's bad, you just drop it and say, well, no, next one. And actually, the filter becomes more efficient if you do it that way. Because usually, when you are running a filter, while you're iterating, you need to dereference twice. First, you are doing your plus plus, and when you're doing your increment, you need to check, does this pass my filter or not? And then you say, okay, it passes my filter, I stop with my plus plus, I'm done now. And then the caller, or your caller, is going to come back and say, okay, now give me the element. But that element is an element you already looked at. That's not so bad if you're iterating over a vector, but if you're running on top of a transform that is actually producing the value, then that may actually be expensive. So here's an any-off implementation with internal iteration. You get a range, and then you enumerate the values in that range. You get the bools in the Boolean context out of that range, and you say result is result or B, and the return your result. Is that okay? Well, we're not quite there yet, because the normal any-off is lazy. It stops as soon as you found something. So you want to replicate that if you do internal iteration. So my first idea how to do this was, oh, okay, when we want to stop, let's throw an exception. That's a very bad idea, because that's way too slow. The second idea was, well, okay, let's just introduce an enum, special enum, that says, do we want to break or do you want to continue? And then the any-off looks like this. You just say, okay, I'm accumulating my B result as before, and if I found one that is true, then I say, hey, break. And you expect your underlying range to respect that. So while he's iterating, you are returning break, then he has to say, okay, that's fine, then we're stopping. Now, the generator range, potentially, we just said here, we want the range to actually heed our hint that we want to break. But if we don't break, if we don't have a function that ever breaks, you can actually elide the break check. So the range can actually, at compile time, decide, does the functor I'm calling, does it actually return that enum, break or continue? If you could return something else, you can just elide the check. You just don't check. And again, so you're not losing performance. This is like the zero overhead principle that Jen Lakos talked about. Now, does this do things in a better way as before? Here's another example. Concatenation. Say you want to concatenate two ranges and then do a for each over them. If you do a concatenate of two ranges with iterators, actually it's not so simple, because essentially your iterator that's inside the concatenated range needs to know, am I still inside my first range or am I already in the second range? And the increment of the iterator is different in either case. So whenever you're having an increment index, then you kind of have a switch on that variant of indices. Here's the variant, std variant of index 1, index 2. So you store either one, and you need to know which one I stored at any given time. And then when I'm actually doing the increment, I need to say, okay, am I now having the first one or the second one? And if you're having the first one, you increment the first one, do the check, and then potentially have to jump over to your second range. Now, dereferencing, again, you also need to switch. You also need to say, okay, either I'm in my first range or in my second range. And you need to do this each time you are dereferencing. So there's a lot of branches, one for the increment index, one for the dereference index. It's kind of bad. You would like to have zero overhead principle. You would like iterate, basically, ideally, the for each over a concatenated range should be just as efficient as the for each of the first range and then for each for the second range. Should be no difference, really. And you can actually do it with the generator ranges. So here it's simple, right? So the operator parentheses is doing the enumeration, and it just enumerates first the values of the first range and then the second value, the values of the second range. And in both cases, it's actually using the same functor as a sink. So you get all the performance that you would want. So the conclusion here is, even for iterator-based, for things you actually have an iterator implementation for, like a concat, at ThinkCell, we actually have, in parallel, a generator range implementation. And then we let the algorithm choose which one it wants to use. So the for each will always use the generator implementation because it's more efficient potentially. And it doesn't need the extra functionality of iterators. All right, so I'm coming to the end. Here is the URL of our range library. You can take a look. It's online. You can use it. And before I conclude, I want to say, I hate the range-based for loop. This thing is a disaster. Why? Because people write this. If all I have is a hammer, everything looks like a nail. If all I have is a for loop, I write for loops. But they could write this. Thank you very much.
Hi there, thanks for the talk. I had a question about, do you support any parallelism in your ranges, or are you thinking about doing so in the future?
We don't, well, we actually, no, we don't right now. We do have a parallel, well, we do parallel for each. I think we have 2 parallel for eaches or so in the program, which, the library is fairly extensible. It works together with anything else you have. So, if you want to plug, say, a transform range into a parallel iterating thing, it'll just work. It'll just iterate in parallel, split it apart into blocks, and then run the transform in parallel. So it all plugs and plays, really. The thing with parallelism is really, I think, is not so much a problem of concepts, at least as far as they are defined right now, but more do you have a good implementation on the platform? And that's currently, I mean, we're still battling with it. So the Microsoft implementation isn't great, and I think Clang doesn't have any implementation right now at all. So that's, I think, a battle that still needs to be fought.
Thank you for a great talk. If I may switch to a more general topic, do you have something like ranges or iterators for two-dimensional containers like tables, matrices, spreadsheets?
The short answer is no. So that's all I can say.
Thanks. Hi, I had a question about the base syntax that you mentioned at the beginning. I was curious to know if you use that in production code, and if you use it when you have several adapters piling up, like transform, filter, and transform. Do you use base? Do you find that convenient?
Yes, you do, and arguably that's what you want. Base is an interesting topic in general. So if I digress a little bit, there is no real one base. It turns out if you're using a reverse iterator, I didn't mention the reverse adapter, which turns out the direction of your iteration, or even with things like filter, you don't always have unique bases. So imagine you have a filter. The filter does not contain some of the elements that are actually in your original sequence. I mean, that's why you did the filter. Now, if you call base, you get the base iterator, but the iterators sometimes have the meaning of a boundary. So when you do a lower bound, for example, on that filtered range, then you get a boundary somewhere inside the filter, and you can't really base it. So there is a weakness of iterators that they don't express whether you mean boundaries or elements inside your range. Now back to your question. Do you want to do this individually for every kind of shell that you of the onion that you put around your ranges? Yes, you do, because very frequently you basically don't know what you're getting. You the programmer knows locally how many onion shells you put around. So a very typical example that we have is this kind of binary search or find, where you transform and then you find and then you do the dot base. There, very clearly, you want to make sure that you are unpeeling exactly the number of layers that you actually know you actually wrapped around it. But you don't know what your caller did. You don't know what your caller, if your caller gave you something already that is a big onion, well, you want to keep that onion as it is and just wrap your shell around it, do your thing, and unwrap one shell. So it seems like kind of a bit clumsy, and there are pictures in the mind of dot base. In reality, that doesn't happen, because locally you are only using one shell, maybe two, but that would be it. This massive stacking really comes about through code like calls, recurrent like calls in where one range get passed to another function, and every function actually contributes something to that range, and that's how you get that large stacking depth. We certainly have 4 or 5, but they are not 4 or 5 happening locally. They are 4 or 5 happening throughout the whole call stack.
Thank you. I enjoyed your talk. I had 2 questions. First, you mentioned if you filter on an R value, you turn the result into a container. And I think on the same slide you said you do this lazily. I had assumed that you would just move the container, the R value into your thing, but that would not be lazy. That would be a cheap operation, but it's not lazy per se. Do you mean it's lazy
That's
after
what
that?
the filtering is lazy. The moving is not. The moving is a move, and you assume that it's O of 1, hopefully,
okay.
and yeah, that's it. So I think no. That's the solution I have. Is you move the R values into that object that's your filter, say, And then only the actual filtering is O of 1, but it is actually generating elements. But it's still very different from doing it eagerly, to do the whole filter eagerly. I mean, that's surely O of n, and that's unnecessary.
All right, that's great. And then the other question is more general. I think you've made some compelling arguments here for why the TS is maybe not optimal, right? What's being proposed and what is moving forward, probably in C++ standard, is not having all of the nice properties that you guys developed. How did it? I assume you talked to this committee and said, you know, you could do some things better. What was the reaction?
So I didn't talk to the committee. I talked to Eric, and we didn't really want to fight the battle. Maybe we should have, but Eric likes his things as they are, and the R value problem he doesn't see really much of as much of a problem. The thing is that what we try to prevent is things going into the standard that would prevent future improvement. And I think so far we've achieved that. So one thing was the iterative validity restricted to the ranges. If you don't do that, I can think of any way how to get this thing to be efficient. So that we actually managed. That we pointed out and said, okay, and they actually changed it. They took it up. There are other things right now which related to. There's currently a requirement in the standard that begin and end. This is in ranges TS. The ranges TS is really just a very basic foundation. It doesn't contain much that is relevant to what I talked about. The implementations of the algorithms with the iterator pairs replaced by ranges, that's motherhood and apple pie. Everyone wants that, and that's undoubtedly fine. There are details in the ranges TS which we actually brought up in the standard in the committee meeting to little success, I must say. They demand that begin is O of 1, which in the normal filter implementation that I showed here, it is not, because you have to find your first element, and that's potentially O of n. They didn't like it because there is a combination when you're stacking a reverse on top of a filter. The reverse needs to repeatedly check begin. And that would need to be, basically every one of these calls, the begin would be O of n. There are several solutions to this problem. So you could say either the filter has to cache the begin, which if you, so either the filter has to cache the begin or the reverse has to cache the begin. But if you are forcing begin to be O of 1, you're really pushing it into the filter. You're really saying the filter has to cache, which actually leads to, in the current ranges v3 implementation, leads to the pretty strange situation that because begin is actually is actually cached on demand. So this thing is no longer thread safe. The filter, Eric's filter, is no longer thread safe. And the begin is mutable. It is non-const. So it can't be called on a const object. I found at this, I mean, I don't want to dispute the general design as at the, like, I don't want to judge it to be the end product, but I think at this stage it was premature to say, hey, we're going to make put the requirement on begin and end to be O of 1. And also at this stage it was just unnecessary because none of the requirements none of the functionality added by ranges TS actually relies on it. There's no reverse adapter. There's no adapter at all. There's no transform adapter. There's no filter adapter in range TS. So this was purely an additional requirement that in my eyes didn't serve any real purpose. We wrote a paper, brought it up to little avail. There may be with indices, there may be a a solution to this problem that avoids it all, where basically you can have O of 1 begin, you can have const begin and thread safety all at the same time in most cases. I haven't explored it yet, we have to try it out in our code base, but it may work. And then it's not such a bad requirement. Then we can live with begin O of 1. I don't know. These are the details right now. And then the ranges v3, I think hasn't really been discussed in great length. So it's still kind of Eric's thing. Anything else?
Maybe it was the last question because we don't have enough time, actually. So, thank you very much for a great talk once again.